Apologies, folks. You just caught me unawares of. Alright, well, tonight's stream is making an adapter for the SpeedX. Now, we made a mistake here. This is despite having tested this out many times. But it looks like when you have a scheduled event, there's one more button to press before you go live. And there we are. That's why we do this. This is how we run. So, anyway, thanks folks for joining. Hi Larry Burr, it's good to hear you. And welcome aboard. So tonight we're going to be working on an adapter for the SpeedX Morse code key, as I put it back together. So the SpeedX Morse code, I got this at an estate sale, pretty much unused from when it was originally bought in the 60s or 70s, something like that. Just covered in dust, fell on the floor as I was pulling it out of the box. So I got it, and really want to use it with my ham radios. It just looks so nice after a polish with some cleaning that I did earlier. Now here's the problem that I have. And there's the key. The problem is that each one of my radios has a different connection on it, and those connections are located on different parts of the radios. So on one radio, I have a very old-fashioned 1/4-inch headphone jack for connecting a Morse code key. I have another type that uses a 1/8-inch 3-ring, 3-conductor headphone jack. And then I have an RCA connection. So if I want to take this key and connect it to these different rigs, I have to make sure that the cable that runs off of these two binding posts is long enough to cover every situation, and it has some unifying connector that then I can attach these adapters to. And most of the time it works. However, I have some radios that if I have them on the table, that if the connection comes from the back, and it does on those, that I have to get either very special short adapters to make it work, or I have to elevate the back of the whole radio or the back of the radio to make sure there's enough clearance, or those connectors and not just have them accidentally bent if the radio slipped. So what I'd like to do is design a common adapter for the key that allows me to switch out cables, and in fact perhaps keep the cables with the radio, and has each individual connection on the radio side, and there's some common type that it uses on the other side. The thought there being I can just buy some inexpensive off-the-shelf Amazon order adapter cables. This one goes to a 3-conductor headphone jack, and this one terminates with a micro 3/32 headphone jack. This is the type of cable you'd actually use with your Bose noise canceling headphones. Okay, so we're a bit accidentally late. I don't want to stream well past anyone who's going to care. So I'm going to condense the last 30 minutes for you folks so we can get to the real meat and potatoes of what's going to happen. So we took a look, I guess I took a look at how the key is constructed and how we could come up with some way to adapt it. And it seemed that it'd be really nice and clean if we had a PC board that could be used on the terminal posts, and allowed us to mount an appropriate. Let's put this model on. Mount the appropriate headphone connector on that board. So here's a model that we did just a moment ago, made out of some cardboard. So we have kind of these combination holes and electrical connection paths on a board like this, here and here, and a relief, just a standard drilled hole in the board for the contact setting screw there. That would still work very nicely. There's no impediment, the action of the key doesn't run into at least this paper model. And we could then mount on one side, either the top here, or we could even do the bottom. We could mount a headphone jack. So we take that headphone jack and just, let's actually draw that here. So let's say that and by the way, these PC board mounting headphone jacks, they look like this. They're typically these squat rectangular boxes. There's the connection. Like that. That either have through-hole connections like shown here. So there's wires that come out of these squat rectangles through the board, and they're soldered to tinned copper pads on this PC board. They also have this in surface mount, so instead of there being wires going through, it would go to connections on the body itself. Say if it's a top mounting one, I think they're about a 1/4 inch. So feel like the 1/2 inch. No. Something like that. Something like that. And generally goes there. Just imagine that connector is there. Yeah, and that could work. So you could get this in a right angle. It could be a straight type, and then it just runs off into whatever cables desired for the radio. And I can get this nice and short if it's coming from the front panel of the radio. I can get it very nice and long if it's going all the way around to the back or up or over, and pick anything I want. Or I can make custom types as I need. It also means I can quickly interchange this, just disconnect the connector, put it aside, and let's say connect up a whole other Morse code key. Say this Vibraplex. Wouldn't be bad to have a similar adapter here too, so we could have the cable just run out the relief on this presentation case. Okay. All right. Thanks, Larry Bird. Okay, so very good. All right. So let's mark this up. Like that, like that. So what I'm doing is just getting this paper model marked up. We're not going to actually take strict measurements off it. We'll do that in a moment. but just want to see what that looks like. We have another viewer. Thank you very much for joining us tonight. This is my first stream, so my apologies for all the mistakes I'm about to make. But with that, I hope you have a great time. And thank you, Larry Bird, for reminding me of blocking. Blocking is important. It's a habit that I'll have to learn. Okay, there's our model right there. That key, put that there. So we want. Hey, Sarah Joy, thanks a bunch. So I got a question. How do you chat? There should be a scrolling chat window on the left side. Yeah, not. Well, I think that's about where my help can take you. Okay. What am I filling in? I know I'm going to have some through drilled holes here and here for these posts. And I'm going to need some sort of area here for making electrical contact to the metal on the binding posts. Larry Bird, thank you very much. I'm all set. I got my tea. And I hope you all have your tea. Here in New England, it's getting very crisp. And I'm already missing summer. Especially looking at all the leaves out there. Okay. So let's say this is a cleaner side. Let's go with this. We want a PC board, and it's going to generally look like that. Oh, hey. Yeah, that's weird. Oh. Sarah Joy, that is, I did not know that is a necessity. That now I know. I'd have to look into that. So back on for blocking. Thank you very much. Okay. I think I like that. So we're gonna have a small PC board. It's gonna be generally shaped like that. This hole here and here, paths for making electrical connection. A just what's called a non-plated through hole. That is, there's no copper around this or on the walls. We want a non-plated through hole here, and this would be about where the connector would go. Okay, and let me just, I want it to say something like speed X and then W1 E U J, something like that. I don't know. Very good. All right, so one last thing I have to do is to make sure that a real PC board is going to fit into this space. So let me get a standard PC board. Go. So what I want to see is when a board fits between, just a second, when the board fits between, is there going to be an interference? I don't think so. Close. So this is a actually this board is meant for one of my radios to replace the bulbs with LEDs, but it's also a standard PC board thickness. So you have something manufactured as a board. There's a standard set of thicknesses that they will typically go, and that usually 62, 63 mils is 0, 0.062 inches thick. Even though they're simple, that's the kind of standard thickness they go. So need to back the key, gap setting screw back down. Something. So I've left out the spring. It's fine. So here, I just need to see how this thing is going to throw in action to see whether there might be. What I would be concerned about is if we put a PC board and it lies here, that this arm or the motion of this screw might get in the way, might interfere or require us to put a funny shape in the PC board. It's really, so that's a really big gap. That doesn't really, no one really, I'm going to say no one, but hardly anyone has that much gap. Something more like a paper thickness. Something like that. Not bad. What I'm going to do is slip that in, and I think you'll be able to see the same. So as this operates, it only goes up. It doesn't really, well, if there's a spring, so it's going to hold it like that. It's only going to go up. So this being all the way flat down with the correct spacing should be as low as this lever arm drops. And what I can see, and I hope you can too, that if this key's set to your typical gap spacing, that we should be fine. You see that little bit of, so what you're looking for is the gap between the PC board and this area here. Because if this key motion was such that it was starting to touch the board, it would start to jam up the work, so to speak. So just like the paper, it's close. I don't deny it's close. It's maybe within a millimeter, but that should fit. Let me put that board away. So the concept is sound that way. Right. So what have we done? We've worked up a concept. We've modeled it. We've kind of tried to poke holes at it. Is there something that's going to cause this to act funny? And I think I've, at least in the short amount of time, thought about what might go wrong. So we did some initial testing. With a model. So one last thing to do, we got to do some shopping. I love shopping. So what we're going to shop for, because really there's almost nothing on this board. What is important is picking the right headphone connector here. So I'm going to go over to DigiKey and show you how I'd search for parts. Great. So we're looking for some headphone connector. Let's see what options we get out of this. Thanks a bunch.
Bye.
All right. So usually when I do a search, I actually learn what they're called, or at least how they're categorized on DigiKey. Just a second. Great. So let's take a look. We got barrel audio connectors, barrel audio cables. Let's take a look what barrel audio connectors looks like. So we have possibly 1,411 to choose from. We can quickly pare this down. What I'm going to use this search for is all the things are, at least to see the scan what's possible for the type of connector I'm looking for. What can I actually buy? So I'll be very interested to click and sort by things that are actually in stock. And then from there, see what features might fit our application best. Some thoughts I have, it would be it'd be good to have a surface mount rather than a through-hole connector, as long as the surface mount connector has some mechanical way to keep it from just being torn off. And the thought there is that it would be nice and clean. It just mounts to one side of the board, and I can actually put it in a reflow oven rather than having to hand solder it. Okay, so 1,411, let's quickly knock that down. I click in stock, and right off the bat, that goes down to 721 options. I'll click apply all to see what that brings us. Okay, well that's already applied. So what's left? Well, I want, okay, let's see. I could have, well, I want a phone jack. I don't want a phone plug because that's what we're coming in with, and I don't want an RCA plug. Well, I did think about that. I want a phone jack. Let's see that. And I want that gender to be female. What else? Well, that still gets us 528 options. So let's think. Usually at this point, I'll start selecting down, because there's a number of options here that are just the same thing but in different forms. You'll see that there's this packaging option. So bulk is just loose pieces in a box, or I guess you get stuff in DigiKey, you get it in a bag. Cut tape. So the parts are loaded in little pockets on a tape, so it can go through an automated assembly machine. And cut tape allows you to get short, small amounts, because this tape is usually spun up on a reel. If you buy a reel, you're in for possibly thousands of parts, and I only really need one. Cut tape you can actually purchase. It's just a cut piece, all prepackaged in this automated assembly tape. Digireel's kind of a mix between the two. It's not quite cut tape. It's on a small reel, but it's not the full size like you get it from the manufacturer. We're not going to look at that. And then some of these other things are tape and reel, that's what we just talked about. Or it could come in a tray or tube. That's just a different way of packaging it, and you can often get that in small amounts. But so I'm going to select packaging, bulk, cut tape, tray, and tube. Still got 521 options. Let's see what that gets us. Okay. Now we can start thinking about what kind of physical layout do we want. Okay. So I'm looking at the mating diameter. That pretty much tells us the size of the headphone that's going to get put together with this. The 6.35 millimeter is essentially the headphone jack. The 3.5 is your standard. Sorry, that 1/4 inch is one of those large, almost 70s vintage. You're plugging it into the hi-fi sort of large headphone jack. 3.5 is what we're mostly using today, and then there's the special smaller type, the It's actually called a sub mini or just a miniature. That's a 3/32 inch headphone. And that's for those special things like old. I think I've seen that the airplanes they use that jack or the smaller audio connector input for Bose noise canceling headphones. Other than that, you don't see it too often. I actually like using that, so I'm gonna pick that as an option, both of those. So I'm just highlighting them now, and that gets us down to 135. Before I hit apply, let me look at the board mounting type. So if I want this mounted on a PC board, it's going to have to be something either through hole, and that's where those leads come to the body of the headphone connector so that it can be soldered down to the PC board, or to a surface mount type where instead of wires they have these copper patches or pads or little legs, so you can lay it on the top surface of the PC board and similarly solder it down. Let me see if I can just sort for surface mount. And of course, it also talks about right angle and still 104. What other options do we have? So we can do, I don't really need a 5 conductor. Don't want a 4 conductor. I want something I can, the mating thing that's going to be inexpensive. And I think that's likely to be a stereotype or a monotype. Pick those. And that brings us down to 39. Anything else? Let's say, very simple. Internal contacts, we just need the connections. We don't need a lot of additional fancy switches and everything else. That gets us down to 18. That's something we can work with. What do we get? We get some nice options. Okay, this is something we can work with. So I have, and that should be coming up for you shortly. But you can just hover over the picture and at least on DigiKey and similarly on Mouser or some of the other electronic component suppliers. You just hover over the picture and it'll come up with a larger view. And this one doesn't look too bad. It looks kind of long, and there's a, I mean, at this point now you're just kind of thinking through your application and what would you prefer to have on there versus something else. I don't want a lot of contacting metal. I'm just thinking well, all the possible radios I could use this with that hopefully I don't use one that has high voltage on the key. That's just, it doesn't matter how the connector is designed. If you have a radio that for some reason did that, you have high voltage potentially on the body of the key. So let's presume that's just not, I'm not building something crazy. All right, so one option is kind of looking nice here. This MJ1 2510 headphone connector. It looks fairly simple. It doesn't have a lot of metal on the body. It has that similar square shape to like what we saw on the PC board I showed you. And maybe able to make that. There's one more way we can see if they give you the option. There's one more way you can sort this to make our lives a bit easier. And this is not something you can do with all components. Many other components don't really give you this, but if we can get CAD models for the part, then that makes our job in producing a PC board design that much easier. Essentially, when you're doing a PC board design, you have to tell the tool what is the shape of my part, where are all the connections, what does it need to have on the board to make those connections, what area needs to be cleared away when you put that part down. So there's a bit of work in creating what's called a library. covering all the details of this component. And you add this component to the library, and you pull that into the design tools to work it up. If we can get those models, then it really makes the job very plug and play. We should be able to take them, upload them to our library, and be ready to use them. All that detail work be taken out of our hands. So let me click on the option for sorting by. Let's see if that sorts by that. How many options? I mean, a similar amount. Okay. So I'll pick the MJ12510. Looks pretty good. So there's a 3D model of what this looks like. Let's see if she loads up. Oh, good. Oh, there we go. I'm gonna take this is better than rushing an order and getting the part in hand just to, feel if it's going to work. So let's see. That's the top. So we're looking down on the board. You can see my mouse. That headphone connection comes in from over here. And it looks like that the solder terminals for the part are here, over on the left here, and here. Let's take a look at the bottom. Oh, here's a detail. If you look at that view, on the bottom, there are two little bumps. And what those bumps are going to allow us to do is if we take this PC board and we drill holes corresponding to where the bumps are, the bumps should press into the holes in the board and prevent what often happens with headphone connectors. Say, for instance, I got that right angle cable hooked up, and I accidentally throw the key across the room, or try to throw the key across the room. There is going to be this enormous torquing force on this connector. And if it was only attached by just the solder connection between the tabs and the copper, just to keep in mind that copper is not very thick. It's a really thin foil that's laminated onto board, and it'll just tear off. The whole thing will just tear right off the board. And really, it could still happen if you had a kind of a wrenching force, but with the tabs, that really should help mitigate at least the torquing by something that's in the plane. That looks pretty good. I like that. Here's a schematic. Okay. So the ring corresponds to that longer section at the bottom of a headphone, and the tip connection is what's contacting this triangle shape here. When you can imagine if the headphone's coming in from the left side, it's sliding through this ring section here, and that ring section makes the electrical contact to that longer bottom section in the headphone plug, and that then the tip. And you'll notice on any headphone connection, there's this kind of little ridge on that tip that is meant to make a contact with this tip connection, like you see here off of pin 2. And what you can use in other circuits is that if that connection's made, you've broken a connection between 2 and 4. And that's often used if you have this working on the same circuit that you have a speaker. And say that if this isn't a radio and there's no headphone plugged in, well, you could have the audio coming in on, say, pin 2, and there's no headphone connector, so the audio goes up pin 2, and then out and back through again pin 4, and then it goes off to the speaker. You plug in the headphone, this pushes that little arm on pin 2 down, which disconnects it from pin 4, so that disconnects the speaker from the audio line, and then all the audio is going through the headphones. So we don't need that in this application, but it's nice. The nice is there. I think it's just that there's hardly any folks I think that need a simpler design than this. I'm sure that if I searched with different terms, I might be able to find something. But this is the more common way to use it. That there's some radio, and you plug it in, and you're disconnecting some circuit when you plug in this external connection, like a headphone. Okay, so scrolling down, first of all, this thing's going to cost me $1.19 in a small quantity. That's not too bad. That price, it's not going to be the most expensive part of the project for sure. And then we have the models. So this is what's going to save us a bunch of work in the layout. Let's see. So we have a 3D model and a PCB footprint. We have this thing that's Snappy DA. Okay, let's go pick these up. Oh, good. So what's going to be helpful? So that PCB footprint is going to save us that effort in the layout. But the 3D model, we don't really need that for the layout, but that could be really nice for getting doing a 3D overall model of the board to see what it's going to look like before we even click on purchasing it. So let's take a look. Okay, there's the 3D model. And they can have it in just about any format you want. Let me take a look at where I'm saving my stuff today. Okay, that's where I'm saving. So let me go then download some. What I've done is I've used this step file format. I think that works with the layout tool that I use. Find out. Good. Let's see where this. I am now just putting it in the working directory. Okay, very good. Now it's I have it. Let's go take a look at that other model, the PC board footprint. Great. So this is the two parts you're going to need in doing a PC board design. On the left side, you have the symbol representation. This is what you'd use when you're putting together the schematic. Here you see a very similar drawing to what they had on the DigiKey website. And this just gives you the same sort of functionality, so you can draw the remainder of the schematic in the schematic capture tool. On the right-hand side, we have the footprint. The footprint is the set of kind of dimensional commands that tells the PC board layout tool all the different features that you need to support this part. So you see in green here, that would correspond to the copper areas we need for the electrical connection tabs that come off this headphone connector. The kind of double outline, that usually represents a couple of things. One is the actual physical space claimed by the part, and then there's one that's the general representation of the silk screen. So often when you take a look at PC boards, they won't just have the name of the part and its general location. So, second here. So here there's a lot of this white printing called silkscreen. And what designers will often do, because it really just makes the job easier of putting this together and knowing what the area will be claimed by the components, is that they will also put the outline of what part, the size of the part, right there. So we have one for each of the headphone connectors, as well as even the capacitors. This is sold as a kit, so that's very helpful for the kit builder to know that this part doesn't belong where capacitors go. At least I hope the 3 leads would kind of tell them that's the case, but there's certainly that this thing is rectangular and this thing is a kind of cut off circle is going to do the job. Sorry. There's a cut off circle silk screen. There's the rectangle for the capacitor. And then the general outlines for the headphones. So that seems to be in this footprint as well, which is really nice. All right, now we can pick what format, and again, this company is amazing. This is, I have to say, this is maybe one of the best one of the best manufacturers to give you options for different pre-made CAD. Often you don't get this many options. You don't get this wonderful format. Very often you have to make an account on their website, which is its own deal. You have to wait for the email to come in, and some of these options, there's usually so much bother. You just go ahead and just take the mechanical PDF and you draw it yourself. But not so here. This is really easy. So we're gonna pick KiCad. That's the tool we're using today. And off we go. Let's see. Cool. So off screen, I'm saving these off to the working directory for the layout. So, my apologies. Okay. Very good. Let's go back to the bench for a second. All right. So we have some mechanical detail about this component here. But we also have to work out what the rest of this design is. Let me just take that away. So we need to know where all of these parts live in space. Live and work together in space. Okay. So what I need to do is just take some dimensions. Very good. So first, let's get some measurements on the key. This one's going to be a bit easier to read. Say we got about 2 3/4 from here to here. And also I'm noticing something. Kind of has a cut off circular shape to it. That's kind of interesting. Let me just try that out. What is the circular shape? Let's try this here, here, here. Yeah, that kind of really does look like a circle. But it could go all the way around like that. In fact, I will. And it looks almost like nearly a 3.5 inch diameter circle. And it's kind of cut off here and here, like that, like so. That helps. It's going to help us when we draw. Going to draw that arc. Okay. So we saw that that was something like, what was it again? Yep. 2 3/4. Something like that. The other one's the same too. Okay. What's it across here? Look. 2 inches. I just have that feeling that I don't know where this design necessarily came from. It looks like one that's been around for since the 1900s, just updated with some improvements. But yeah, this really looks like this was designed in the United States, all to inches and standard shapes, circles, rectangles, very, very simple angles. Okay, 2 inches across there. All right. How far from here to here? Okay. Let's see. I'm going to say about, wow. Just a second while I get you in the shot for this. And to my eye, that looks like 1 1/8 inches. Like that. And then we have the gap setting screw somewhere in there. Where does that compare to everywhere else? Okay. So what I've done is to remove it completely. I'm going to pivot this down a little bit. The other way. Right. I just need it to be flat and about kind of through the middle there, like so. Okay. Let me actually use this one. This vintage tempered ruler, like so. And looks to me like it's a little higher than 1/4. Take a look. This part is fun. Say it's about here. Use my marker. And it's about there. About there. What do we got? Apologies if I do this off. It's 3/8. I mean, yeah, that looks about 3/8. One and 1/8. That's 3/8 inch And one of the last things is I need to know what size these screws are. I had a nice tool called a wire and screw gauge. And there it is. Okay. Here's my wire and screw gauge. So on this side, you just rest the wire, it'll stop going down, then you can read off the gauge off of that. So this screwdriver comes in at about, looks like about not gauge 9 or 10. But we're not doing that, we're doing screws. Where do we come in? We're looking at the number on the right side, and it's about looks to be about a 6. So common American size would be a 632. 640 is another type, and that last number is representing the pitch and number of, sorry, the kind of number of ridges, I guess through screw threads actually, that you would get per inch. I think 32 is less, 40, being literally 40 threads per inch. Okay, so those are 632. So I want to have whatever holes we have, they have to allow a 632 through just to drop in. And while this is a 632 screw, and it's a little tough, I have measured this before and it is all the way around 632. This hole that has the pass-through for the gap setting, that has to be larger because we expect that screw, as you push down, that it's going to kick out. So we don't want it to be the same size as this, in fact a little larger. All right, so what's a 632 screw need to have a pass-through? Let's take a look. Okay. So here we have the tap and clearance hole chart, and on here, that's the 632. So on the left side, we see the screw type, and what we're looking at across is they give what tap size. If you were to make this using what's called a tap, it looks a bit like a squat, kind of a combination of a thread and a corkscrew. That actually will form the threads in a metal or other material. But we don't want that. No, we want the size. Oh, sorry, it's the drilling you need to be able to tap it to put threads on. Mistake. No, what we need is a free fit. Free fit means that a screw would just very loosely pass through. It's not going to be real close. It's not going to potentially get bound up, and we do need that because these screws are not, in the post, are not precisely built into the body. They can, if you haven't buttoned them down really tight, they can float around, so they're not very stable or precisely in their location, whatever this 1 1/8 spacing is. So a good free fit is what we want in the hole, we want that to be we want to free fit that. And looking at the chart, it looks like we would want a number 25 drill, and that drill would produce a 0.1495 inch diameter hole. Let's just call that 0.15. and that would be for this one and this one. Now, a lot of the libraries we're going to run into that have pre-made holes, they're done in metric. So let's just quickly look at the inches to metric conversion. Okay. So just for our own 1 millimeter is 0.0394. And it's kind of running down. We see that a 4 millimeter is 0.01575. So if we find something that's about a 4 millimeter or slightly less diameter hole in one of the other libraries, that'll work quite well. In fact, that's a little bit even more open than maybe necessary, but it's not too bad. I think that would work great. So either a 0.15 millimeter, 0.15 inch diameter hole or 4 millimeter. And we know for the gap setting screw that that's going to need to be something larger. So let's say that could be even 0.2 inches, perhaps, maybe even 0.25, so 1/4 inch. Or that could be something more like 6 to 8 millimeters. Those they don't directly convert, but I think that should be good enough to work with. Okay. Some last things we have to figure out is geometries. We have this, we have this, and we know where they are with respect to each other. We also kind of know that they're going to be centered between the two sides. And the last we want to consider, we don't actually need to necessarily know how close it is to the edge here, because we don't really have any constraints, or at least not too many constraints. We don't want things so close that the body of the connector might interfere in this region here. But what's definitely going to happen is that we need to have enough we need to make sure that our board is not so long going off the back that it runs into these pivot arms here and here. So let's get that measurement. So looks like actually if we come in about the same, that an edge can't be any further back from the terminal post screws, about 3/8. Okay. I think that's something we can work with. So we know that this cardboard piece is going to be roughly 2 inches, like so. We know that this has to be 3/8, like that. We know where these are with respect to each other. And we just need to make sure that the whole thing is long enough that the back of this does not interfere with this. And really, that's one of the other things we get as a help from the Model 2. If we made this PC board like this, and come in house. So from the corner to that corner, about 1.25 inches. So something like that. I think I can work with this. Let's get into the design tool and lay us out a PC board. So I'm using KiCad. It is a free open software tool, free open source software tool that's quite mature and has a wide range of libraries and is well supported by a number of manufacturers. So if we're getting into PC board design, I can't recommend it more. Let's head over. Okay. So I'm not going to give a tutorial necessarily this that I'll be here for quite a while, but I will let you know as I'm going through what I'm doing, why I'm doing it to some degree, and hopefully at the end to see the results. And that if you're interested to do more, please feel free. There are a number of wonderful tutorials out there on using CAD, including ones from DigiKey, but certainly a wide range of sources. And you'll find that library support is out there. You can, of course, design out your own components using the tools here as well. But it's always more helpful to start if you can get things like libraries from the manufacturer or from free and open source sources like GitHub and the like. So I'm going to create a new project. I'm going to call this, actually I already have it, NV SpeedX adapter. That's what it is. NV is Viking, the manufacturer of the key. Let's call it NV. Okay, and there we go. So you'll see that by default they create a blank schematic and PC board. So what we'll do now is get that part that we had downloaded from the manufacturer and get that into the footprint library and the symbol, that representation of what it is in the schematic, in the schematic library. So I'm going to start with the footprint. Hovering over here, here's footprint. Right. We go there. It comes up to the footprint editor. Let's see. All right. So I'm going to add that footprint. Create footprint, add library, import footprint. So we have something that already exists. I had already created this library called VPG connector. So all my stuff, I just give my initial, and then it's almost like a subheading of the type of components that are going to be used here. And I'm going to import that footprint, point it in the right location where that downloaded one came from. It's kind of interesting. Did it get broken? I think it did. It's pretty stuck. Apologies. Let's try that again. I see it. Okay, very good. So, right. Let me go to the location. Okay. We are going to open up the KitKat dash mod file. Let me just bring this window over. There we go. So you see KitKat underscore mod. That is the file extension for footprints. So let's do that. See what we got. Oh no, it crashed it. Oh geez, that's great. That's what I love. crashed it all the way. Just do it again. And for folks who are watching, thanks so much. I would be doing this because I do want to have this adapter, but I'm really glad that you folks are able to join in and watch. Feel free to chat in whatever format, and I will try to answer your questions as they come up. We'll try that import footprint again. So I'm gonna go over here, and there we go. All right, there we are. So that's the footprint. It looks very much like we saw on the CUI website. And instead, what we have represented, the red are the areas where the footprint, this literal footprint, where the contacts from that connector are going to be soldering down to. The red is the copper, the kind of what's called the pad, where that soldering is supposed to take place. We also see that there's numbers here. Those numbers are the they don't correlate to what we saw in the schematics. You remember we saw 1, 2, and 4, if I recall. Here we see just 1, 2, and 3. But they do correlate to the schematic symbol that will go with this. So we have a footprint. There's a schematic symbol that says, okay, this is the ring terminal, this is the tip terminal, and this is the switch. Those numbers will be the same as what's expected for the actual physical part. So I'm going to guess number 1's the ring terminal. We also see in the teal color, that's, I believe the teal color is the silk. Yes, it is. It's the silk screen. So that is very much like we saw on the other on the other board, where they screen on the general shapes. You know, that's the part that goes right there. It goes in this orientation. We see a white. So the white you don't see in the actual part. The white's used in something called an assembly drawing. If you're handing this design over to someone to build, you don't necessarily give them this enormous and what was traditionally an expensive tool to just open to see what the board is generally laid out. You'd make a drawing called an assembly drawing, and that would have its own representation of what the parts are. It's not all parts are appropriate to actually border with silkscreen. In many designs, there's no room to do that. It's just too complex. It also can, I don't know, but it just seems like it would get costly, more complicated. And there are requirements. You can't silkscreen like right up against a part. But what the assembly drawing layout can give you is the ability to print out a PDF that has where all the parts are supposed to go. So you don't need that silkscreen. You don't need to literally print it on the board. There is a print that carries all that same information. This actually was the traditional way to represent this for assembly. Now, unless you're doing it by hand like I am, the related digital file for placement and orientation, that's what actually get used, because most parts are not put on by hand anymore. They're put on by a robot. And all they need to know is the X, Y position and which way the part's supposed to go, versus what the part's orientation in the tape and reel. Okay, so that's the footprint. And in this tool, all we need to do is save, and we're going to save it to my library. And that's fine. Okay, let me just do this here. And away it goes. So I'm doing this layout on the same machine that I'm doing the streaming. So it doesn't usually take this long. Hmm. Okay. That is getting upset about my paths, so my apologies. See if I can sort that. All right, so what's happening off screen is I am sort of just I'm turning off some private libraries that are likely interfering with the saving operation. So if everything goes badly here, I have a whole other. This is like what I suspect always happened with Julia Child. Just in case, there's a whole other turkey in another oven that I can pull out, and I'll show you the design completely worked up. Okay, let's see how that turned out with my stuff. Okay, did that take? Didn't seem to spit fire. Oh no. What are we gonna do? Okay. Okay, there we go. We got it. Very good. That's the footprint. There we go. The CUI MJ1 2510. That's our connector. It's a footprint, ready to use. So we're all saved and we can close out of the footprint editor. We've imported the model. It's available for use. Now let's handle the symbol. So permit me, I'm going to pull this off again off to the side to manage my libraries, just to prevent what we had just happen to us earlier. My private libraries, which are not available, giving us some issues. Thank you, Sarah Joy. That really is a delight to hear. Because I don't want to pull the other turkey out. I want to show what happens. And I actually kind of intended that with this. I'm not giving a tutorial. I would like you to see the general process, including all the fuck ups. So, because usually there are two ways to learn things, and one's the blessed way, I think. If you're clever enough, if you're smart enough and lucky enough, that you can see it, you can see or understand something, just kind of based on the little bits you're offered. And then there's the other way of learning, and that's because you tried something and it didn't work, and you understood why it didn't work. That there's still some cleverness involved, but I'd like to think that at least in my hobby work, and I'm going to be honest, a little bit of my engineering work, that it's just my value, where I've gained what I had is just because of the thousands and thousands and thousands of mistakes in my past. It's just that I've tried so many things. I'll know what doesn't work. Okay, I'm talking too much. Let's get working. I want to import a symbol. It's the same one we downloaded. Look at that. It's right there, ready to go. Boom. Look at. I want this. I want the properties. I'm gonna do here. It's my preferences. Yeah. Let me see this. So I just want, I don't know. It's nighttime. I think I'd like that to be all black. Find it. Display options. Don't spend too much time on this, David. There's other things to do. Okay, I can't find it. What do we have? So we have something similar. This is going to be very much like what we see dropped onto the schematic. There's that ring over here. It goes to pin 1. There's the tip connection here. That's pin 2. And then you see the one they had on DigiKey that said pin 4. Here it's given as pin 3. I don't think that's going to matter as long as the footprint in this agree. There's also a bunch of text that's all over, all mushed up. Let's do this. A bunch of other stuff. Huh. I don't know what that is. Manufacturer recommendations. Okay. What's really important here is the green stuff. So the green is the letter J. J is the typically the. So when you look at a schematic, and we'll see a little bit, but you see a schematic, components don't just give their general name like Harry, Sue, John, Taylor. They often get given some sort of designator because if Harry, Sue, John, and Taylor are all part of the Smith family, then they're all in the Smith group. So connectors, they're in the J family. J is the letter that has been historically used to say this is a connector. So you look at J3, that's the third member of the connector family for that design. Then we also see the part number, manufacturer part number, MJ12510, and then the pins. You also see this word passive. If you're doing some more complex routing in this design, where you needed to have power traces have certain characteristics, like they have to be a certain weight and they have to be a certain width, you can help hint that by setting what the pin type is. And similarly, if you're trying to control what sort of ground systems they hook into, that's more into design we're not going to get into. If it's passive, it's fine. It's not going to stop us from doing our work. And I did not want that to go to the amplifier video live. Let's say that instead. Now, let's do a new library instead. Okay. Let's do NV. I think this stream and competitive knitting are probably neck and neck for breakneck pacing. I think so. Okay, I like it. Let's go with it. Can I do it? Yes. Yes. And there we go. Where are we? Where's my pen? I can filter it. Nothing there. No. Let's just see if I can just do it again. I have I have used this tool before, and I do designs, but what I'm not used to is I'm not used to doing it on essentially my downstairs TV, because right now I have a setup where I have the laptop, I have the downstairs TV, I have the chat laptop going behind me. Uh, I'm in a I'm in the Matrix right now, and so and also you folks are all watching, which just makes it harder. It's an amplifier video. Me save a copy as. Stop putting pressure on me, man. It's too much. Okay. There we go. Save. Get that pop up, and I think that gets the footprint. There we go. That's the symbol. That's in. Uh, There's the library. There's the pretty. The pretty is for the footprint. There it is. All right, I have one more thing to do. This is where, because I already made the turkey in the other oven, I want to show this before we get to the board design. I mentioned that it'd be good to have, going back to the bench top, it would be good to have the right sort of holes. And let me see if I can find an example. Okay. Yeah, right here. So here's one PC board. And what we want to have is that structure where there's a hole drilled in the middle, and then there's this really wide area that's tinned, and that's the electrical contact right there. This is an example of what that actually looks like. There's a very fine hole. It's meant for the lead of a connector to go through, and a small annular ring of tinned copper, and that's the contact. That's where the solder actually will melt on and somewhat weld to. So what we're going to do is look at the footprints that give us something like that. We're looking for something called a mounting hole. And I don't, unfortunately, have a good example. Here's an example of the other type of hole. So we want a mounting hole that has an annular copper ring like this, but we also want a hole that has no copper at all. In fact, the copper should be pulled away. And that would be a non-plated through hole. That is to say, there's no copper around it, and I don't know if you cannot see, but I will tell you, these holes that go through, they're actually plated, and there's metal inside that forms the plated through hole. So when solder, so you stick in a wire, let's actually use solder as the wire. You stick in a wire like that, you know, that molten solder will flow. It'll attach and weld to the copper here. It'll attach to the copper in the hole itself, which also makes the electrical tie to the back. So if this was very old-fashioned board, like 60s and 70s, maybe 50s, you'd have a circuit on one side and a circuit on the other, but they wouldn't be electrically connected. You would have to take a wire literally and push it through, and then solder both sides to get a connection. Well, the plated through hole prevents that. It also makes a very robust connection because not only it's just a little bit of attachment, but also the wall of this board as well. Okay, so let's take a look at some of the options for what we can use for holes and just get those selected ahead of time before we even go into schematic capture. Just take my hat off. Thanks, folks. And so I'd say we're going to try to make it quick, wrap up at 10 o'clock as much as we can. We may have to do part 2. I really don't want to pull the other turkey out. Okay, we're going off to KitKat land. And let's look at those footprints. Mounting. Here we go. There we go. Yeah. So it's just typical. So let's see, we got a 2.2 millimeter hole meant for an M2 screw. The yellow is the hole, and that's just a hole. You see that yellow color? That is representation. Let's see. Yeah, kind of representing the mechanical drilled out area. And then there's this blue and white ring. So that white ring, I believe, let me see. That is a drawing shape just showing where, if you're going to use this with a screw, and that screw head's going to have some width to it, that's the area that's going to take up. And then similarly, there's a kind of mechanical outline drawing in white, this thin white that tells the same, akin to what I mentioned with the assembly drawing. So you can print something out without having to literally print it on the board. So we need 2 types. So that's just one where there's a hole and there's some area that represents that we should keep things out of, because we really can't put components over here. It's going to get mashed by a screw head or a standoff. Here's another type. So this hole, it's just this iris kind of black hole over here. What we see happening in this one is this surrounding annular ring, and let's see that. Let me highlight that actually in green. Turn those off so you can see what's going on underneath. Somebody's yelling out there. You're doing it. I know. Why am I not getting this? Okay, that is, yeah, that's representing, that's just copper. So we got everything turned off. That's just copper right there. And that copper is surrounding the hole, kind of akin to that same area where you'd have the screw head contact. So this could be useful for those terminal posts. So if the hole is large enough to have a nice loose slip fit with the screw of the terminal post, and then this surrounding area, which will be done with tinned copper, that's what makes the electrical connection. So that's called a pad via. So you can drop it down, it leaves a hole, but you can actually use it like an electrical, kind of a terminal board electrical connection. So we're going to look for ones like that. Let's see something more our size. So I said that those terminal posts should be either 0.15 inches or 4 millimeters. And that one looks good. I mean, could either have a 4 or 4.5. Let's go with the 4. So we know that later on we're going to need to call this out. And this will be for those 2 terminal posts. Okay, let's look for something that's either 0.2 to 0.25 or 6 to 8 millimeters diameter for the gap setting screw. I'm going to say something like that. Yeah, something like that. I'm going to make sure to turn this all on. There, show all layers. There we go. Okay. All right. Yeah, this will work. So the yellow here is the drill through hole, and then there's a related keep out area. You don't necessarily need that keypad area to be represented that large, but that should be fine. Let's go with that. Okay, mounting hole 6.5 millimeter. We'll use that for the other one. Cool. We're quickly going to run out of time, so let's keep going. That's good enough. Let's work on the schematic. So the typical way you work on a design that's not just stuff manually drawn onto a PC board is that you will do the schematic, and the schematic will produce what's called a net list, and that's just the computer's representation of what you drew on the schematic. That gets brought over to the layout tool, and in the layout tool we can take this representation and then physically lay out how stuff connects. It actually allows you to not have to keep track of what pin goes to what pin. It already knows. That's what the netlist is telling it, and it'll prevent you from doing silly things like connecting the wrong pin to the wrong component. Now, if you mess up on the schematic, that's, well, sorry, that's on you, but at least the tool helps you along the way. All right, so this is going to be very quick. We're going to have just a handful of parts and only one real part, just the connector, and then we're going to call some other parts. So let's go smack in the middle. And let's look for that. I think it was something like MJ. Yeah, there we go. There it is. There's the part. That's our connector. And we're going to zoom in. Save. And let's put down some of those. So what I know ahead of time is that mounting holes you can actually put down as parts as well. It's not always the case, but it often is. So there's that mounting hole pad. That's that type, as I said, the mounting hole pad is that one that's going to make a nice annular ring for a mechanical electrical connection to the binding posts. So I'll put one here. Let me copy that and put another one here. Maybe I should drop that a little bit. I could put down. I mean, it's just clean. So I click this green line. I'm going to be, that represents a wire connection. So I'm going to put a wire connection between here. Oh, whoops. Look at that. I'm a little off. Let me move this. Okay. So I skipped a number of steps. So I do things like set my grid for the kind of drawing I want to do to keep it nice and neat. But this design is simple and time is short. So we're just going to go forward, and if something gets in the way, then we solve it. So there's a connection between pin 1 to this mounting hole pad, and that's what's represented in that green there. Let's do the next for the other. And there we go. There's another. So there we have it. There's the connector. There are the terminal connections using the mounting hole pad type. The other thing you can do, and it actually just makes it that much cleaner, is we can actually do the same thing for the other mounting hole. I can even show it sort of how it's going to look on the real board. Kind of like that. It doesn't connect to anything. It's not a pad, so it doesn't have to connect to anything. There's a tool in this schematic capture called design rule check, and one rule check is, have you connected all the pins, or have you represented the pins not going to get connected to? The mounting hole doesn't. Okay, so right now we just have a schematic representation. It has no physical information about what the part is or what its footprint is like, the mechanical and the like. So I'm going to associate that stuff now. So I'm looking and, oh, good. So this thing already has the footprint associated. So I'm looking here as the footprint, and that's calling out that it sees that footprint. Let me just make sure. It looks fine. Okay. Now, how about, now we do have to do this for the mounting hole because there's so many different options. Yeah, see, it's not picked. I'm going to pick something. Mounting hole. We said we liked the, what was it? The 4mm? Yeah, Advia. And there we go. Now it knows what size it needs to be. I'm just going to copy that and do the same here. And now it knows what part it needs to be as well. Great. So then that's the easy part. And there's this, oh, we do have to one thing. You mentioned we have to tell it if something's not going to be connected to. And it's this X place a no connection flag, and that's what's going on. Okay. That's it. That's the schematic. You can even center it. There we go. All right, so now we're going to, so what we see have, let's see, yeah, what we have going on is you see these J's and H's, they just have question marks. So as you're laying out this schematic, every part, you're not going to necessarily say, okay, that's J1, J2, J3, because you might go in, cut entire sections of the schematic. Now a whole swath of numbers are gone. And who wants to go back and reallocate those? The tool's going to do that for us. It's going to say, okay, you're done with the schematic enough. You want to give it all connector, mounting hole. You want to get those enumerated. So we'll click on annotated schematic. Everything looks there. And now if we close it, this is J1. It's the only J item on the schematic. And then there's H1, H2, and H3. That's usually one of the things. It won't let you even move to the next step until that's sorted out, because you need this done to generate the netlist file. That netlist file is going to say, okay, J1 pin 1 connects to H1 pin 1. They can't do that unless it knows what J or H or whatever part is on there. But we've done that. So we're going to generate the netlist now and save it. There we go. Off it goes. Finally, we could do field materials. I think we have enough. So we can just go and open the PC board editor. So we're brought into this abstract theatrical space. And cool. Hey, whoever joined us, thanks so much. I hope you can drive some fun. So what we're working on tonight is a small adapter board for the SpeedX. So a PC board is going to carry a connection to allow us to take any commercial off-the-shelf adapter cable to connect to the variety of rigs that I have at home. And for those not in the ham radio world, rigs are what ham radio operators call their radios, or setup radios, or pile of hazardous waste that's connected to antenna or whatever it is. All right. So we're in this space. This is the space we're going to draw everything up for the design, the outline of the PC board, where each part goes, and then from there we'll produce the outputs, which will be what we'll send to the board house, which I'll be able to see show you on the stream. to actually produce our boards. And we actually should also be able to see a 3D model. So I did have the paper model, and that worked well enough. But this tool will show you along the way what your board looks like in 3D. So you have a really good sense. And you can actually take that and see if you're doing something more complex, you could incorporate that into a mechanical design. But first things first, we're going to load that netlist that was produced by the schematic tool. Oh, I see what happened. This is one of those mistakes. We go over to, we didn't assign a footprint to this thing. So that was that we wanted the 6mm hole, I think. Just a regular one like that. I think that'll work. And then I can go back here and update the PCB from the schematic. And it's not giving me an error message about a missing footprint. And we update it and we close. And look at that. There's our parts. There's those two mounting hole via pads. Those look like we expect. And then there's the hole for the for letting the gap setting screw through. And let me just move this. That's not associated. But if I move one of the other actual electrical components like this, see those rubber bands that are kind of peeling off from the parts? Those are what's called the rat's nest. If you had more parts on here, it would look like a rat's nest of wires. The rat's nest shows you what pin is going to what pin, so that you can come in, you know that needs a wire to go to there, and you just kind of almost connect the dots if you wanted to. So what I'm about to do is this, I'm literally drawing the copper between these two parts. So click on it, there's the trace, skinny trace, and then down there, and now that's connected. That's done. And what you're trying to do at the very least with this layout is for the entire net list, make all the connections, eliminate the rat's nest, and then everything's laid out. You also have to make it work and not throw errors about things interfering with other things. But that's not where I want things. We have to draw the outline first. Okay, so I am going to draw, use edge cuts. And, okay, something important here. To be able to quickly put together these designs, especially where you have something that has these really standard dimensions like 2 inches, 2 3/4, and 1/8, is if you set your grid, you can pretty much just kind of drop these lines without much effort. I'll show you an example. So if I pick 100 mils, that's 0.1 inches. And make sure I'm still set to edge cuts. I'm going to draw a graphic line. So if I clicked here and there, let's see, this was 2 inches across, something like that. There, okay. And then we wanted this to be, let's see how long. We want it to be 1 1/4. That's 1 inch. Okay. So I can actually just quickly drop it down using a really coarse grid. So I'm just going from point to point to point. It won't let you make spots intermediately. You have to set a very fine grid. You can turn it off, but it just makes layout harder. Go to 50 mils. If I set it to 50 mils and draw myself a line, starting from the end of my last one right there. So you look at the bottom left. Do you see that length? That's 1 inch that would be 1.5. What I really wanted was 1.25. And there we go. All right. And then similarly, 1.25, like so. So this here draws most of the rectangular part of that PC board design that I was interested in making. So I gotta get a sip of tea just a second. I think not. Okay. Oh, that's the sound of the terminal screws falling on the floor. That's all right. It's fine. All right. So 3.5. Now we want to draw that kind of nice arc over here. So what I want is I'm going to just draw a temporary line here. I think that's a little high. Watch. Draw that here. Let me pick something in the midpoint here. Mind, I'm just kind of do this like I'm sketching it out on paper. I'm sure there's a quicker, rational way to do it. Just not off the top of my head. But that that kind of circular diameter that the base of the Morse code key had, that was 3.5 inches in diameter. And what I'm going to calculate now is we had a radius coming from the middle of that out, what would that be? So 25 divided by 2, 1.625. That's that appropriate grid. That should do it. Again, there are other ways to do this. You can use a CAD tool to draw this out. Typically anything more complex, and maybe even to this level, should have been done that way. What I'm going to just go for is just draw myself, say 1.625. Draw myself a line that's vertical. It goes up there. It's further. Let's see, can I draw the arc that way? I feel like I may have slightly done it wrong. Let's go for it. Let's try. Sorry. Something like that. That work? Cool. All right. Bad. I think it's approximately correct. Good enough for the job. Kind of gets that shape I was going for. And then let's click that. I don't need it anymore. We'll leave that line there. And I'm just going to put, we knew that the centers of the binding post holes had to be 3/8 off this bottom edge. So 3 divided by 8 is 0.375. Down a line. Oh, it's only the last time I give a mea culpa. I just really want to quickly see something not work first. 375. Right there. Something like that. And actually, what's really nice is that it really does hint strongly when it's vertical or horizontal. Like it'll even though it didn't need to, it almost like finds a way to jag the lines. Okay. So that you see that it's not the right angle. So this upper line here, that should be on the centers of those mounting holes should be there. So let me just bring those parts down. So stuff like that. Let's take our connector, let's put that somewhere. That top nub, that's the actual jack entry point for the plug. There we go, like that. And somewhere, feel like somewhere there. We're gonna, you know what? See that rat's nest? We want that naturally that there's going to be a trace going down that right side. So let's do that instead. Okay. And similarly here, just come on. And then finally this guy. Click M, that moves it, so it's going to be somewhere about thereabouts, roughly. So we don't have it routed, but we might be able to see what this actually looks like. Okay. Well, it's rough. Okay. There's those binding post connections. There's the hole for the setting screw. It's size larger than it needs to be, but and then there's the connector. So we see that the connector here is just represented as its. So you see that white? That's its silk screen. And it's literally kind of floating in space. And then the pads are what's in silver. All right. So it's complaining that it doesn't have a complete. That's fine, because we haven't finished. This yellow's the board outline. So we said that the terminal posts are a certain space apart. That's 1 1/8. So 1 1/8. 8. 1.125. Apart from each other, divided by 2. Oops. 1.12. I am using calculator I found at a yard sale. And now I know why it was there. All right. So that's something spaced like 0.562. We'll get close enough. So we want to be out further. Okay. Move. Let me do this. This is smarter. 0.5625. That should do it. What I'm looking to do is hint where where it is. There we go. Okay. It didn't help. There are certainly easier, smarter ways to do this. I never choose. Apparently. Okay. Similarly there. So another way we could do try that. It's not thinking too much about it. Is set another line. Because we're going to delete these lines anyway. So we'll look at the length. Right. We're looking for 562, and it's down at the bottom left. And we got it. We even do this. There we go. All right. Now we move this guy, and oh, can't see it. It's not as helpful. Not quite there. And usually when I do this, I find more clever ways to use the grid to just essentially force me to put the part where it needs to be. So one way to do it was to set the grid so that the spacing essentially was some number of clicks where I need it to be. Another way to do that is to actually set them as a combined pad. Because these two always go together, that's actually a total footprint. That takes a bit more work than I wanted to spend. Okay, those are close enough. They're spaced from the back. We have that arc. We have this connector placed fairly well. Now we just need to make sure this is centered and spaced enough from the line going through the middle of the contacts. Okay, so I had that as 3/8. 0.375. Let's see if I can hint it. Just center it there. And then go. And then we'll move it up. Okay. Forgive the quiet. Graphic one. Just graphic line. There. Again, smarter ways. Look into them. But slowly it creeps up. So that's a little long. And there we go. So we want that hole to be about there. Oh, good. I see it. Okay. Let's get that away. There and there. And it's saving. There we go. Okay. Close enough. We don't need. Oh. So I'm going to remove these graphic lines. I don't need them anymore. And it's actually going to start to recognize it as a closed shape after this. Should recognize it as a closed shape after this point. I removed the interfering graphic lines. No, okay, there we go. Okay. Not bad. Let's see how it looks in 3D. Huh. I was kind of freaking out on that, on this arc. No, it all looks pretty good. Hmm. So, okay. That looks fine. That looks fine. That's weird. That all looks good. And that all looks good. All right. Mysterious to me, but okay. Well, let's add some copper. So as you get this tool, it just gives you one standard width, because everything's going to be two-dimensional. You're just going to get what you call it to be the width. The thickness is set by design. If you ask them to make it out of, they don't term it in thickness, but rather they give it by weight. So you call out for 1 ounce copper, that's 1 ounce per square of area. Actually, no, is it like per foot or something like that? It's some large amount, because essentially it's if you take that copper and if it was a literal weight, that's how much it would weigh. But I believe it's something like 1 ounce copper comes out to be 0.7 mils of thickness. You don't have to worry about it. You essentially you get the thickness by calling out the weight with the manufacturer. And typically it's also the thing that will determine what your pricing is. So the last dimension left is you have the thickness all sorted. Thank you very much, Sarah Joy. It's slow going, and it looks like I will have to pull the other turkey out, but thank you for joining in. But we'll see. We're gonna go as far as we can with this design, and then we'll go on to the one that actually works. We're going to change the trace width. here. So I'm gonna call it some widths. So right now we have the default 9 point, some weird number. Well, let's call out 10. And this is literally, we're going to say, okay, I want the option of just a standard 10 mil, that's 10 thousandths, 20, 30, 50, 25. I just don't think I'm going to have anything that big. Let's go with that. That's a lot of options. What does 10 look like? That's pretty thin. What does 30 look like? Now, these circuits are not going to carry a lot of current. They're just, well, if this was the turn of the last century, they used to carry an unbelievable amount of current. Those Morse code keys were big. They were built in shields. They were often built on pieces of marble, ceramic, anything insulating, because they would have to switch large currents, but especially high voltages. These keys, of course, don't have to do that. That hasn't been a thing for a long time. I think the Widowmakers are long gone. Anybody who has one knows it, and if you ever talk, they're like folks who they restore those old vintage engines from those ones they used to use for running washing machines, like those. They'll tell you every little detail, and the folks who have those radios are very much the same. They'll tell you every little detail, including that it has to be a particular key on a highly insulating base made of marble, so you don't get shocked. I don't think everybody else gets shocked by it too. Okay, so what does 30 mils look like? Still pretty good. Oh, 50. That's okay. That's good. So they don't have to be wide. Like I said, you can think them, this flat copper strip is like a flattened piece of wire. The currents these things have to take is minimal. It's just enough to tell the radio to actually do the real work of turning on the transmit circuits, producing the RF power, and then sending it out. So it doesn't have to be big. That's fine. Right there. And then similarly for the other one. Now you see that it kind of does this snaky dance like that. Okay, we'll zoom in so you can see the snake dance. Like so. No, don't touch. So this is the trick and the beauty of a layout tool, as opposed to taking a piece of film and marking it up with a marker like they used to do 50 years ago, 60 years ago. This tool knows that this trace has to go from this pin to the highlighted pin on the left. It's also making some recommendations because generally you like to keep a very organized design with your trace. It's also probably easier for the computer to make straight lines and bends than it is wacky curves. Actually, no, that's the case. But it kind of hints, if you want to go down this way, you do that. I do notice that if you go in with a certain orientation, it gets a little wonky. So sometimes what I'll do is I'll get pretty close and then click, and now that upper right part is now fixed. That's not going to change now, but this part might. And I click that, and now that's done. And at this point, this design would be pretty much complete. Let me fix a couple of things though. So we noticed that there wasn't a 3D model for the connector. We can change that. So I've just opened up the part back in Footprint Editor, and I'm going to go to Footprint Properties, and we're going to go to 3D Settings, and we're actually going to load the 3D model. I just have to go find it. Oh, oh, it's thinking. Oh no. Here we go. Pray with me. Let's hope it makes it. Please don't die me. All right, we win. Fantastic. All right, so we're going to go to here. Should have a model somewhere. Yeah, there we go. There's the step file. Cool. All right, there's a 3D model. Let's take a look. That's the wrong way. I don't think it's supposed to go on that way. No, I don't think so at all. Yeah, it's obviously turned around. It's not oriented. Connector's pointing out the wrong way. So this stuff on the left side is rotation, offset, and scale. This is where you can take the model and tweak it to actually fit the associated footprint. So I think this is about a rotation, mostly. Let's see what happens if I... No. No. Let's go back to that view. Let's see. Alright, so what is supposed to happen as I click on these rotations, the part should be similarly rotating as with respect to the footprint. And it does not. It's a bit weird. Let's try. There we go. Let's turn that off. Let's dump it. There we go. That fixed it. Turn 90. Let's turn that 180. Turn that 90. Okay. Still not quite where we... Oh, that's too deep. So look, it's going right through the board now, and it's not where it's supposed to be oriented here. So now we're going to do the offsets. About there, it looks like it's about 5 millimeters off. And then the Z, we're going to look for the whites of their paths. Let's see. So it's floating in space. We're going to drop that down. And now it's better. Not bad. There's those nubbins. Remember the nubbins I talked about? They're right there. There's the holes already put into the footprint to handle it. And then there's the connector. You'll see that a connector falls within the silkscreen. And that model should be ready to use. Let's save the library. I think that got it. Good. Let's see if there's some sort of update. Update footprints from library. Yeah, so this now is going to pull in that change. Yep. And we got it. Now it's going to still give a problem with the arc I made, so I'm kind of mystified by that, but let's take a look. All right, yeah. Well, there it is. There's the part on the board. So I'm going to do one last thing. So we have an option. excuse me, we have an option as to how to present this. We can actually tell it that the solder mask color is going to be black, because that would look slick. And there it is. That's black solder mask and all that. Let's go back to the drawing. So if we've got this board, it would just be pretty unadorned. So we're going to now put on some text. And we don't want that in copper. Although you can actually literally have text etched out of the copper that's on a board. But instead, we're going to take this silk screen, and let's say we'll put it here. There it is. And I'll put my call sign, W1EUJ. Do that in the silk screen as well. You know what? That needs a little bit more. Hold on. 2020. Here. That's it. Okay. How does that look? Yeah. And there it is. There's the text. It'd be printed out in white. Not too bad. Okay. So we're getting to about 3 hours into the stream, and it's also about where my voice starts to give out. So what I'm going to do is we're gonna call the design sorted out enough for tonight. Next week, we're going to have a number of things happen. One is that we should actually get, so what I'll present during the first part, I should say, is the remaining part of the PC board design after sorting out the issues, completing the layout, making sure all the dimensions go right. Because what we're going to see come out of our design is something like this. Just a second. What I have is a paper model of the completed design on the bench. Oh. This is like what you saw on the drawing. There's the connector here. There's our binding post connections. There's the hole. And I also added another component. You didn't see it in the design work we did, but I added a small capacitor. This is something that used to be included for old rigs of the 40s, 50s, and 60s. I put it there just in case, because we're having it done. But very much like what we designed, I took that completed design, I printed it out on a piece of paper 1-to-1, and I cut it out, and that's what this model is. Because what we're going to do now is, before we go to the step of doing a PC board order, we want to make sure it actually fits and looks something like what we want it to do. So I'm just going to slip the part in. I'd cut those out with the method you saw earlier in the video. Still have one binding nut left that's not on the floor. Okay. I'm going to drop the screw, and you're going to see the screw goes through. No problem. So it's an oversized hole, and the way that the this arm moves, means it's going to kick out, but you can see it's quite a bit of space. And let me just make sure this is, yeah, quite a bit of space, passes through quite nicely, and there's enough room to allow for that kicking out. Not too bad. Yeah, it's really quite nicely centered in my eyes here. That connector would mount on top here. If there was a capacitor, I'd put it here. And what should happen when we connect the cable is that that cable goes in like so. And now that free end just goes off to the radio. So it looks like we got a good part that looks nice on the 3D model. I've put in an order for that, so next week's stream should actually next week's stream is going to have quite a few things. You're going to see the part, you'll see the PC board, you'll see the process through which we completed this design, uploaded it to the PC board manufacturer, and went through what they call the design rule check. So that's where they run through your design using their automated tools, make sure it can be done with the process that you've wished to purchase. And usually how that works is inexpensive boards have rather large tolerances. Really complex boards have a lot of layers, because you can have more than 2 layers, right? You can take this copper and laminate it and have copper on both sides. That's 2 layers. You can take 2 of the boards and laminate them. That's 4 layers, and you can go from there. 6, 8. Well, desktop computers had quite a few layers to them, but of course that's a business that costs more money, and they put engineers on the case to even check all that. But we're doing a very simple design. It can go through an automated tool, and I'll show you how to go to a common a hobbyist provider called Oshpark, how to upload your design and get that to go. You should actually see that board for next week. So we'll assemble it and actually, in the end, try it out as well. So I'm checking any issues? No, we're still streaming. That's great. So first, I'd like to thank you all for joining me tonight. This, again, is my first stream, so I kind of knew that I'd run into issues. This is a learning process, and this is how I make my mistakes to learn, like I mentioned. And I look forward to streaming more Sunday nights about 7 o'clock. You'll see if you subscribe, and I would recommend you do. I do plan to do more videos over the winter, where we're all going to be stuck inside anyway. Yep, we'll be starting at 7:05 on the weekends. Sorry, on Sundays. Well, you'll see more. So that's our project. We're going to wrap it up next week, but I want to show something else. So earlier in the stream, I brought out this old key. It's called the Vibraplex. So the Vibraplex is invented in response to what would happen with folks who are using this key. So you have, and they're young guys that would be hired, paid not a lot, to send messages on the lines, between city to city, sending telegrams, later on between ships and ships to shore, and they would over and over and over and over and over and over and over again, and they would get what was called then glass arm, essentially carpal tunnel syndrome, from this repetitive singular motion down. Some people get some not. Some keys were better at preventing it, some not. But in response to that key, which has been around pretty much since the beginning of telegraphy, this key was designed around the turn of the century. So first thing it does is instead of making it a downward motion like this, it made it a side to side motion like this, which automatically, you could even kind of get into a rocking motion too, like that. Way easier on the wrists. The second thing was to take half the workload off the sender. So with the regular Morse code key, every time you close it, that's when the current would flow, and that's when you'd get, depending on how long you held it down, short dot, long time dash, long time, trying to get someone's attention, I think, or trying to test the circuit. Anyway, so what this key does is it takes half the work away. If you push it this way, right over here, it's just like, and in fact, looks like a Morse code key on a side. That's how this actually was invented. This used to be from a kind of a hack where guys would take two Morse code keys and bolt them to the table on edge like this to go like that. It's called sideswiping. Let's just say it's one of the reasons sideswiping was done. There's a lot more to it, but I'm gonna spare you the lore. But the whole other bit here is magical. So if you push it this way, you see that vibration? Actually, a little easier if you really open that up. This arm swings out this way, down, and it vibrates, which is kind of where they get the word vibraplex. As it vibrates, these two contacts here contact. So if we had this hooked up to a transmitter now, do this, da, 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 do here, I just have to hold, push and hold. It's making dots automatically. And it'll make dots for quite, I think at most you need 6 dots in any reasonable communication. And this will make 6 dots if you have this thing set just so, for any high speed you want to set or send at. So that worked great. It changed the motion to more of a swiping, rolling motion, and it did half the work for you. And this was invented turn of the last century, and they are being manufactured for ham radio operators to this day. So that's cool. But actually, when you have this thing set up, the slowest it will go is something like 20 words a minute. And I already got this big weight here to try to slow it down as much as possible, because really, you either change the weights or push the weights out to make the arm vibrate slower. But still, for me, not slow enough. I'm still something of a slow sender. So there are tools that have been around for a while to make this go slower. They usually, well, one of them is actually this, to get a bigger weight. So you could get multiple weights and then really slow it down. Another was to take an arm. This is called the varispeed. Say one operator wants to send pretty fast, so you want to set something to make it go fast, something like that. And you want to go slow, like that, but the arm was out on a weight, so it's in a way pushing the weight further out, which would really slow it up. And you could vary the position there or here. What I have, it was my other recent project, is a very nice, clean, inexpensive way to push that weight out further, to make this thing go really slow. And it's here. There's a video, and I'll include a link after I do the edits on this stream. There's a fellow who has reviewed a number of keys online on YouTube, and he had a very nice design for taking off-the-shelf tubing from the hardware store. This is aluminum. This is nickel-plated brass. Take standard materials and cut them like so. So one is an aluminum tube. There's a piece of, sorry, it's an aluminum tube with a piece of dental floss going through it. And the other is this solid nickel-plated brass rod. This part will slip onto the arm. And the dental floss, which is this Teflon-y stuff that they have currently, just kind of adds a little bit of friction so it doesn't slide off so easily when you're working with it. Slip it on, and it just slides on like so. There we go. Now we've really extended the arm. That nickel-plated brass rod here is the same diameter as the original one here. So we'll add that weight like all the way out. How about that? Something like that. So this whole construction's really not going anywhere. And now this thing is really slow. But it does require some adjustment. So there's a couple of, well, first of all, there's a problem that this trunnions out way too far. So it's never going to damp enough. So you see that it still kept, there we go, that's better. So this is more my speed. So not bad. That'll work. You have to remember this key was invented for telegraph operators turn of that century. So even though the weight could slow it down, it was meant to go at line rates. And one of the many reasons you hired these young kids is that their wrists were in good condition and that they could send fast because time is money. Time still is money. But hammer operator is not doing it for money, doing it for the love of it, especially with CW, sending Morse code. It's for the love of the sound of it, the flow, the magical words kind of floating out of the ether into your mind. And so there's no, like, the rest of your life leaves you unprepared for doing that unless you operate quite a bit. I unfortunately don't, but I think it's a benefit to you all because you get to see the bench project I do spend my time on. But it still means I send a bit slowly, so a tool like this is going to help. All right, well, thanks so much for joining me tonight, and I wish you all good health, good luck, especially for the oncoming week, and I hope to see you next Sunday, 7:05.